Hello there. My name is Robert Platt. I am a professor of computer science at Northeastern University. Today, I want to talk about recent work in my group on end-to-end learning in what's something called spatial action spaces. So before we get started, let's just take a look at where we think we are in terms of accomplishments in robotic manipulation. So there's grasping, there's novel object pick and place, and then ultimately domestic tasks that we want to try to solve using our robot. So I think it's fair to say that there's been some exciting recent work on novel object grasping. So whereas 5 or 10 years ago, the predominant approach to robotic grasping was object segmentation and then shape fitting a complete geometric model to the object and then executing a planned grasp. Now there's, I think, growing acceptance that grasp detection has a role to play there. So what is grasp detection? Well, essentially grasp detection takes as input raw sensor information. So in the case of grasp post detection that I'm showing here, the robot takes a point cloud shown in the lower left-hand corner as input, and it returns the 6-off position and orientation of various different hand poses in the world with respect to the point cloud that the robot expects to be able to execute a grasp from. So what's cool about this is that, contrast to prior approaches, the robot doesn't need specific prior geometric models of the object it's going to grasp, and it works remarkably well, I would say, in clutter, like what we've seen here. So the segmentation task in this sort of domain is just extremely challenging, and this kind of a system is able to grasp in spite of that. Now, of course, there are downsides to this kind of approach as well. So one of the reasons this thing does so well is that it's not relying on a segmentation or shape completion of the object, but that means that it's more difficult to tell this system exactly which object to pick up if the objects are densely cluttered. And perhaps more importantly, it's hard to express to the agent exactly how you want to grasp something. So if you were planning on a grasp on a geometric model, then it's easy to express to the robot, well, this is how we need to do the grasp in order to perform the task. But if you're not, if you don't have a full geometric model of the world that the robot is interacting with, that kind of approach becomes more difficult. So a key question with this kind of approach to grasp detection, to grasping, is how do we use it in the context of more challenging or just longer time horizon manipulation tasks? And I would say this is an open question. There's been some significant work in this area under the heading of task-oriented grasping, but I think that it's hard to know how to express, how to know how to grasp something in order to perform a task unless you have a good handle on the manipulation task itself. That is, how do we plan desired grasps in the first place? And I think that while we have a good handle on how to do grasping, and it's not perfect, of course, but like I said, I think there's been a lot of progress. We do not yet have a good sense of how to reliably solve open world manipulation tasks. So manipulation tasks requiring a series of steps, whether it's just pick and place steps or something, or non-prehensile, more complicated, over a longer time horizon in order to perform some task. So even something as simple as doing block construction, like I'm showing here in the middle of the screen, it can be very challenging because of the stability of these structures. And of course, policy learning for domestic assistance tasks like making coffee for a robot assistant in home, that's obviously very challenging too. So yeah, so when I think about this problem, I often think about it in the context of household assistance tasks like the coffee making problem. So in this problem, the robot is given the robot needs to make coffee, but we want to be able to solve that task in the context of novel mugs. So we don't necessarily have experience with this particular mug. We want to be able to put coffee in it nevertheless. Novel coffee packet geometries, novel coffee machine geometries. We want the system maybe to be able to adapt to different types of machines or different ways of actuating the machine. And we want methods that obviously can operate in an unstructured world, at least, be able to adapt to different placements of the coffee machine in a kitchen environment. And I think given there's obviously been a lot of work in the field on reinforcement learning with application to robotic applications. And I think the central question here is, what role should end-to-end policy learning play? Things like reinforcement learning. Do we solve the coffee learning problem? Should we be solving the coffee learning problem by using unstructured end-to-end policy learning alone by itself without any other assistance? Should we structure the solution? So we're still doing policy learning, but we're structuring the solution somehow, maybe via residual policy learning, maybe via learning from demonstrations or some kind of demonstration structuring the policy, structuring exploration for policy learning. Or maybe we shouldn't be using and learning. Maybe we should be doing the old-fashioned traditional planning methods that have been made more relevant by the recent progress in segmentation and shape completion. So maybe all we have to do is traditional planning methods with better segmentation and shape completion methods. So this talk, I think this is a really critical question for the field of robotic manipulation. I'm interested in all of these topics at the bottom of the screen here. What this talk focuses on is an approach to end-to-end policy learning that focuses on exploration via some kind of demonstrations. I'll talk about that more later. Okay, so in order to try to structure our solution space, gonna do a lot of evaluation on block construction tasks. That doesn't mean that block construction tasks are the end-all be-all, but for now they are a stand-in for the more complex real-world tasks that I want to be able to solve. And these tasks can be very challenging. It's challenging. We'll be doing construction with more than just blocks. So just grasping the objects can be challenging. Placing them stably can be challenging, and knowing how to build the structure so as to maximize the chance of success is challenging. Of course, the hope is that we generalize to real-world domestic assistance tasks. Okay, I'm going to introduce real quick 5 different ideas that kind of come together in an approach. Okay, the first is something that has recently come to be known as spatial action spaces. So the idea here is that instead, so for policy, we need some action space for our robot to reason about what we're gonna encode a policy, and the policy has to be over some action space. The question is, what should that action space be? Most, if you open up reinforcement learning applications to manipulation literature, you see most applications, let's say OpenAI, GEM environments will have actions that correspond to something like end effector velocities, joint velocities, etc. We think that this is maybe the wrong action space because it just it means that you're going to have to reason over very long time horizons in order to solve moderately challenging tasks. What we do in this talk is use something called a spatial action space. In the spatial action space, we formulate a very large action space comprised of tens, hundreds of thousands of actions, where each action corresponds to a reaching motion of the robot's hand to a distinct position and or orientation in the environment. So if you imagine the space of all positions and orientations in the environment that the robot could reach to, that is the space that's the action space that's available to the agent. So, of course, the downside of that kind of representation is you've got an action space that has hundreds of thousands of actions, or spans essentially spans SE3. So that's potentially a problem. But the nice thing, potentially nice thing about that encoding for action is that you can express a trajectory that solves a moderately interesting problem, like one of those block construction tasks or the coffee making problem, in a relatively small number of time steps. So we can think about making coffee inside of like maybe 10, 15 time steps instead of hundreds or thousands of time steps. So that's significant. Some of these policy learning methods have trouble over long time horizons. Okay, so we're going to use a spatial action space. So again, the action space is maps onto SE3. Each point in SE3 corresponds to a different action, a different place that we could move the end effector to. Okay, hopefully that was clear. Second idea is, and this is something that's been in the literature for several years now. The idea of using fully convolutional neural networks to encode Q functions. So let's just take a trip back down memory lane to the basic network structure for DQN. So we take as input an image of, let's say, an Atari domain. We have a convolutional network that outputs values for a set of nodes where the number of nodes in the output corresponds to the number of actions available to the agent. So this neural network encodes the value function, and each node on the output corresponds to a different action available to the agent. Now, if we are going to have an action space with hundreds of thousands of actions, that means that there's lots of nodes on the outputs, and that's potentially a problem because it means that our network complexity has really gone up. But there's a simple solution here, and that is to use something known as a fully convolutional neural network. Takes a depth image, in our case, a top-down depth image as input, and it produces a feature map with the same dimensionality as the input image, but the semantics of the feature map are such that the value of each pixel in the output map is equal to the Q value of moving to that specific XY location. So each point in the output of this fully convolutional network corresponds to an XY position in the world, because this is a top-down view of the world. And this fully convolutional neural network is encoding the Q value of moving to that location. Okay. So you see here in the lower left-hand corner is an image of some partially constructed block structure. And over here, going into the fully convolutional network is the top-down image of that block structure. On the right is the Q map, which is telling you that the sys is telling the agent that it needs to pick up the block in the lower left-hand corner in order to proceed. Okay. So this idea is, I think, a pretty simple idea, is surprisingly effective at solving, somewhat interesting manipulation tasks. So here, we're just stacking 4 blocks on top of each other. But I would note that if not for this action, this would be a very challenging task to learn if you had to reason over hundreds, maybe thousands of sequential delta XY actions or delta joint motions in order to solve the task. Now, we're not doing everything here. So this agent is only able to reason over a two-dimensional action space, just X and Y. So it's just reasoning about what the XY coordinates should be, and it's using heuristics for the rest of the dimensions. But I think that the potential here is maybe clear. So we can't rotate the hand. We can't reason about how high. We can't do anything out of plane. But at the very least, we can solve, a potentially interesting task. So I think that's interesting. Next idea is to leverage an idea that's been in the literature for several years. It's been in the literature for decades, really. Something known as the augmented state representation. So the idea here is to to develop a method of handling the full six-dimensional action space instead of just using an XY action space. And before I go further, I should say things like actor critic or DDPG, PPO, et cetera, with, those algorithms can use a high dimensional, can have a high dimensional action space, but they do very poorly in these kinds of tasks because the actor in those systems has a hard time with the complex multimodal nature of these action environments. So we've looked at DDPG and PPO, and these results are in our papers. That's just a really challenging. That's just really challenging to get those kinds of architectures to learn anything. So here we're using this augmented state representation to try to handle the high dimensional action space. So the idea is that instead of specifying the full six-DOF action in a single go, we're going to decompose that action into a sequence of steps. First, we're going to select an XY coordinate to move to, and then we'll move to some kind of intermediate state. Then we'll select the theta location, orientation to move to, then we'll move to some other state, and then finally we'll select the rest of the dimensions and we'll move to the final state. So the sequence of these three partial action selections is equivalent to a full action selection at the top. In the original problem. And it turns out that you can re-express the problem this way without without changing the optimal solutions or changing the optimal value function. The only thing you're really doing here is you're getting a much smaller action space, because it's no longer a six-dimensional action space, but it's like the union of a couple of two or three-dimensional action spaces. You're getting a much smaller action space at the expense of creating more additional states into this. So there are these additional augmented states. That's the price you pay. But deep networks are actually really good at handling just a larger augmented state space. So that's actually not a huge burden for modern policy representations. Okay, so here's our system. So we're reasoning over the full six-DOF of orientation. The first level selects XY. The second level selects theta, just a single direction of orientation. The last level selects Z and two dimensions of orientation. And there's some complexity here, which I probably don't have time to go into. Essentially, the top level is functioning as the fully convolutional network I spoke of before. And then there are these two additional levels that make sequential selection of the additional orientation and Z position variables. So what does this do? Does this work? What does this give us? So this actually works really well. This is surprisingly well, I think. So this kind of approach enables us to essentially learn policies in a six-DOF in a six-DOF action space, meaning that the agent can reason about to move its hand to any position and orientation potentially in the environment. And so we're demonstrating this in this video here, where the blocks are placed on these ramps in order to demonstrate that it's able. The ramps are placed at random orientations and positions. This is just demonstrating that the system is able to perform the correct pick action on the correct object at different out of plane orientations. Okay. All right. So good about this, we can work in 6-DOF action spaces. Bad, we're still solving simple block structures. What can we do to scale up the complexity of the block structures we're trying to solve? This brings us to an approach to imitation learning, learning from demonstration, that we call here planner cloning. So the idea is that there is some kind of a full state planner that operates in simulation that is used to solve the problem, the block construction problem or the coffee making problem, whatever the problem is. There's a planner in simulation that can solve that problem from different initial instances of the environment, and it generates lots of expert experience, which can be used to train the policy via some imitation learning method. Now, we've developed standard imitation learning methods like DQFD. Don't work super well in the high action space domain, so we developed a variation which does called SDQFD. That's probably all I'll say about that. But we're able to effectively do imitation learning in these domains. And what this gives us is the ability to solve more complex structures. So imitation learning, learning from demonstration, this is important because it enables the agent to do better exploration. In the sparse rewards in some situation, which is what this is, the agent only gets rewards when it reaches the goal, not at any other time. You know, there's no structured reward function here, no reward shaping, no curriculum learning. The agent needs to, the odds of the agent stumbling upon the goal is essentially 0. So we need some kind of demonstration in order to guide exploration of the policy learning agent. And that's the role that imitation learning, planner cloning is playing here. All right, last idea is, I guess, a standard idea in policy learning, which is training over a variety of object shapes and domains. So here, we want to, obviously, we don't want to just solve block construction domains. We want to be able to solve challenging manipulation problems involving novel shapes. So in this setting, what we do is during training, we randomly sample object shapes. The job of the agent is to build a target structure using a set of randomly sampled shapes. Now, they're not sampled completely randomly because they have to have certain characteristics, like there has to be a roof there has to be some small blocks and a big block in order for it to build this structure. But the agent is, it's figuring out which blocks should play which roles, and then how to grasp those blocks, how to stack them, and how to complete the structure. So this demonstrates that the approach, it generalizes to the novel object setting. So this is important. You know, going from known objects to novel objects, that's the place where end-to-end learning, we hope, is going to really show its advantages. And in fact, it does, because with relatively little effort, we're able to go from simple, standard, easy to detect blocks to more complex objects like we see here. All right, so this method, as you know, we've shown videos of the robot actually doing this. So all training is in simulation. We introduce some noise, essentially a form of domain randomization to accommodate domain transfer. Since we're using depth images in combination with that type of domain randomization, our sim to real problem seems to be relatively mild. So this, essentially, the policies that we learn in simulation seem to transfer to the real world, I think, extremely well. So you see the success rates here. So these are task success rates. So what we're seeing here, this 97% means that out of 40 times, we ran this 40 times from random initial configurations of these objects in the world, and it succeeded 39 out of those times. This is pretty good. So that means that we can perform that sequence of grasps, that sequence of places in the correct order without falling over. 39 out of 40 times. So we're pretty excited about that. As far as we know, there are no other approaches to policy learning that don't rely on some kind of segmentation or object detection that can do this, have this high a level of success on these kinds of tasks. So that concludes my talk. Thank you for listening.